So figured we'd briefly cover one of the more popular forms. Well, the most popular form of kind of very basic machine learning and predictive modeling, just a simple linear regression. And I think in general, it kind of falls, when people first get into building models, linear regression should be your first real attempt. It's very easy to interpret. It matches up with what most people think of when they try to think of like something predicting something. You build exactly, correlation. What's up? Yeah. And a lot of times you'll be surprised that a linear regression will still be the highest performing type of model. Maybe you'll have to change the variable, like one of the input variables into the output, like the thing that you're using to predict the output. So say you're using like something simple. You say you're using like K percentage to predict ERA, right? Like any model out there will have something like that, like some form of how often a pitcher gets whiffs will factor into his performance on a runs allowed scale, right? So a lot of times, like maybe that itself, like, the K percentage, because that'll range from like 15% to 35%, and the ERA will range from 2 to 5. So those are on the same scale, but people transform variables. So maybe it's shifting it down by a variable or shifting it down by a constant, applying some sort of operation to the input variable, so forth. Like a bunch of times, like a popular one is applying the log of the variable, and then all of a sudden to linear scale that way. A ton of times linear regression will still work out the best, and maybe you bring in multiple variables, you build a larger model out. So I think oftentimes people are too quick to hop from linear regression to more complicated stuff, neural nets, a random forest, whatever the situation calls for, or whatever like you think will make the most sense. So I kind of want to cover a couple good situations to use linear regression in, and to attempt to at least exhaustively like get a benchmark from that. Because if your newer glossier model can't improve on top of linear regression, then you're not really doing that much, right? You need to go back and look more into what your variables are and their nature. So
Dan got a question about like
yeah. So that's actually one of the things that made me think of it, and I'll cover that briefly. Dan got asked a question about loess versus linear regression, and loess is basically like a locally weighted curve. So it's like you essentially it'll look like a kind of a polynomial regression, but only because it fits to each of the local points. So
it's kind of like a rolling average, right? In
a sense, yeah. Like so it'll be like fit to the population might span across a range of X values, and then the curve will fit the actual value. So like a good way to visualize it, if you're familiar with geometry at all, would be like sine cosine. Like a sinusoid is like very locally weighted, right? Because it undulates up and down based on like where it is in terms of the X variable. So the like original LOESS curve kind of approximates a sine wave. I think it's technically called locally estimated scatter plot smoothing, and you can apply different weights to it. You can weigh like certain like X ranges more heavily, so it overfits to that. But a linear regression is just like a straight line, and might be positive, might be negative, might be flat, like in which case that kind of tells you that linear regression isn't the best thing.
Right.
So a couple things I wanted to kind of cover over. The assumption should be that whatever your transformed input and output are, there is some sort of linear relationship, right? So if you do put it on, if you can get any sort of linear regression that's not close to flat, then I think it's like worth investigating. Right. A lot of times the idea is a lot of times you'll see a lot of noise. So a lot of times like noise might mean outliers, might mean like there's a ton of jitter in the points. So if you can figure out if the noise is like that's what it is, if it's just like a little bit of noise, or if the outliers actually mean something. If it's just a little bit of noise, that's natural when building a model. And if you can figure out a way to smooth that or remove the noise, then linear regression still makes sense. If, however, your outliers aren't actually outliers and like, those are legitimate values that will keep reoccurring, in that case, linear regression probably doesn't make sense because it's just going to try heavily overfitting the outliers or not keep those in mind. So if the outliers are in fact legitimate data points that you need to account for, linear regression doesn't always make the most sense.
Right.
Another time it doesn't make too much sense is if you have multiple variables and there's a lot of collinearity, which is something I've covered in the podcast before. But collinearity is when the variables itself help explain it like another of the input variables. So in my previous example, if you're building something to account for like runs allowed or ERA or whatever, like kind of proxy metric you want there and using K percentage,
mm-hmm.
if you're using K percentage and K to walk ratio, clearly those are pretty heavily collinear, right? If you have a high K percentage, you're probably also going to have a high K to walk ratio. Obviously, they're not the exact same variable, right? Like K percentage just accounts for how many whiffs you get. K to walk ratio accounts for, how often you're walking hitters as well. But there's going to be a ton of collinearity there. So if you're using linear regression and using variables that are collinear, those will often overfit. So that you want to make sure you have variables that themselves explain different parts of the variance of the output variable. And another big thing, another two big things that I've actually kind of talked about before is metric normalization. Linear regression is often heavily helped by normalizing everything, having everything on the same kind of scale. So going back to my previous example, even if it doesn't make sense at first to visualize a relationship between K percentage, because that's between like 15 to 35%, and ERA, which is between 2 and 5. If instead we normalize all that, so the ERA and the K percentage is on the same scale of like -2 to 2, -2 to 2, where 0 is the mean of each variable, that will often help you make better and more consistent predictions. And it'll also be a huge benefit, and this kind of goes hand in hand with what I said, when both the input and output variables have a normal or Gaussian distribution. So when they follow like a traditional bell curve, that'll be much easier to build a linear regression. If it's like a skew distribution where it's like a long tail or most of the data is concentrated in one area, you'll often find that linear regression is not the best move. So one of the things I do usually when building...
If it is a normal distribution, that linear...
Normal distribution will help with the linear regression, yeah. Because like a way to think about it, if you like visualize like a steady line and a bunch of points sprinkled throughout, most of the points will be concentrated. Most of the points will be concentrated like in the middle, spread out, they thin out.
Right.
If all the points are like concentrated here, kind of a big clump, and then only a few here, the linear regression, like that big middle section of the linear regression will be like based off very few points, right? Because it'll be it'll be swayed by where like a few points are in the meaty middle section that's missing way more data than it would be if it was normal. So that's kind of like a quick overview. And just like to bring it back to applicability, one of the very first things I do when looking at a possible like multi-variable model where I'm bringing in multiple variables to predict one other variable, and Brady's seen me do this over my shoulder when I was doing validations for KVS and BLAST and DK, is just build a huge pair plot structure. And I probably mentioned it when I in that episode too, where I'm looking at each variable against another variable and just saying like, okay, do these have a linear pattern? Do these have a distinct non-linear pattern, right? Because the worst is kind of it's just like noise. If it's just like a blob of points, it's like, okay, maybe I ought to rescale a variable, or maybe there's nothing here. Maybe it's just straight noise. But it's really important to be able to tell if certain relationships, because if one had a log relationship, then I could take the log of the input variable, and then it would be I'd be able to apply like a pretty high performing linear regression. So case in point, just summarize or just always make sure, whether through a scatter plot or whatever kind of visualization you want, try to understand what variables share a linear relationships, which ones share a distinctly non-linear one, and which ones are just noise and going to be hard to account for with whatever model you choose.
What would be like the, I guess like the big harm Of, I guess, going to a polynomial too early.
Overfitting.
Just overfitting.
Overfitting like a motherfucker, yeah.
Yeah.
Because this thing about, even think about like the simplest like polynomial, like say x squared, right?
Mm-hmm.
Y equals x squared. And then like it's good through 3 points. And then like when it's like 4, it's like, holy shit, that's shooting up,
Yeah.
Can I ask my question with ASMR? What do you say the proportion of regression models that you use are linear?
Kind of an interesting question, because a lot of times, I mean, pretty decent proportion, especially because a lot of times what I do is, rather than spending like multiple days on finding the absolute best model, we're just looking to like validate like proxies, So a lot of times we're like, okay, does this correlate with this? So if I get that question a bunch, right? Does this correlate with this? So in that case, I'm trying to put it on a linear scale, or at least help explain like, oh yeah, it correlates with this up to this point. So disregard crazy wonky values outside of this range. In this like kind of bin range, it correlates with it. So I do like quite a bit of, like, I don't want to say, like it's not even like full blown out models. It's just answering discrete questions by trying to look. And I think Lindley, I think you can attest to this too with some of the R&D requests you've been doing. Yeah. Right? Like a lot of times it's like, rather than build out something that not perfectly, but minimizes the RMSE or minimizes whatever error proxy you're doing, you're just looking at shaping certain variables in relation to each other, and then being able to look at it and be like, okay, does this make sense? Is there something there? And so in that case, quite a bit, right? Because even if there's like a log relationship, you can easily take the log of that and then make it a linear one.
So like it's it's like a good first check to see if there's any relationship between you. The other thing that I was asking, is it still considered linear regression if you transform a variable but with a log or like some exponential maybe? Like, is that, you're still using a linear regression like test, but if you were to make a model based off the log of one of the variables, you wouldn't, I don't know. I think previously I wouldn't have considered that a linear relationship, or like, I guess there's a difference between linear relationships and then using a linear regressional model. Yeah.
It's a little bit, it can be a little bit boiled down to semantics, I guess. But the way I look at it is, if your end output model is a straight line, that's a linear regression, right? Yeah. So if that includes transforming one of the input variables to the log of that variable, you wouldn't say the input variable and the output have a linear relationship, but you say like the transformed one and the output have a linear relationship.
Yeah, that makes sense. Fire.